So in this lesson, we tackle some applications of these accumulation functions and some function analysis involving these accumulation functions. So these problems are a little bit higher level than the problems we've seen in previous lessons, but they highlight the exact same skills. So make sure you have your notes handy from previous lessons because that will help you out on these for sure. The first one is a function analysis problem, and it's pretty straightforward, I'd say. So the question is, does g have a relative minimum, maximum, or neither at x equals 2? So we're going to be looking at this point in the graph. And then we want to explain. Okay, so make sure that your explanation matches the one we generate here too, because we want to make sure our reasoning is clear and clear enough for the AP graders to give us points. So g is an accumulation function. It's given here, right? So g is the function, the integral from 2 to x of f. So g is the area underneath this graph between 2 and whatever x we're plugging in. So let's remind ourselves what we're talking about here. All of these minimums and maximums are going to deal with the derivative of g, g prime, right? At a minimum, g prime should change from negative, so decreasing, to increasing, negative to positive. At a maximum, it's the opposite, positive to negative. And then neither would be obviously neither of these two things. So obviously we need to figure out what g prime is. We have g. Taking the derivative means this accumulation function sort of cancels out. So the derivative of an accumulation function is just whatever's inside the integral, the integrand it's called. G prime of x, we'd say, is just equal to f of x. Graph that we have is f of x. So we're looking at the signs of the graph around this point. Notice positive on the left, positive on the right. So we'd say neither, right? Because the derivative does not change signs. So you want to say two things in this explanation. So you want to say g prime of x, the derivative of g. You want to show that you know that that's what we're looking at for this analysis, is equal to f of x. And we can even say that same thing, g prime of x equals f of x. Does not change signs. At x equals 2. Okay, so in your explanation, I'd be looking for two things. I'd be looking for this, the fact that you know what the derivative of g is, and then I would be looking for it does not change signs. Okay. That one I think was pretty straightforward if you had your reference and if you understand how to take the derivative of this accumulation function. We'll move on. So number 2, we want an inflection point of g. And this gets a little bit harder. So we have to remember where an inflection point happens. An inflection point of g is going to be where the second derivative now changes signs. And again, you should have that in your note. You should be starting to memorize that at this point in your calculus career. So inflection point means this. It's where the graph of g would go from concave up to concave down. Now, we need to figure out how to write down g prime of x, or sorry, g double prime of x, the second derivative. Well, we have the first derivative. The second derivative is going to be the derivative of that. G prime of x is equal to the first derivative of f. So what we really want is f prime of x to change signs. Okay, so there's a couple of places this happens. F prime is the derivative of this graph, so it really is just the slope, right? So we're looking for positive versus negative slope. And I've switched colors now to avoid confusion with what we were doing with just the graph of f. So looking at just the slope of this line, this slope is positive here, and then negative here, and then positive again after x equals 2, and then negative after x equals 4, and then positive as it increases down here, negative again. So we have options here for our inflection points. We can go with the first option, so x equals 0, or x equals 2, or x equals 8 are all fine answers. So x equals 0, x equals 2, and x equals 8. So these are inflection points of G. Okay. So two kind of on the easier side function analysis problems. Again, make sure you know what you're looking for with the graph. So f is the derivative of our function. So this is a derivative graph. And then for our inflection points, we're looking at the derivative of this derivative. Okay, number 3, here's where they start to get a little bit more challenging. You got to do a little bit of reading. So we're waiting in line for a ride at Six Flags. There are 700 people in line. I don't think you will be, but don't be attracted to this number 6. That's the name of the park. Doesn't have anything to do with the problem, right? Now, people are arriving and getting in line at a rate r of t. R of t is this function here, so it says r of t is the graph. People enter the line but don't leave it. And we want to know the number of people in line for the ride after 3 hours. Okay. So, a couple of keywords here. This word rate, that means r of t is a derivative, right? So you can think of it that way. R of t is the derivative of the number of people in line, right? It's the rate at which the number of people in line is changing. Okay? So after 3 hours, what we want is the total number of people that get in line from 0 to 3, which would be this integral of r of t. Okay, so now we have to think about how we can solve that. Well, it looks like all we have is a graph, right? So let's tackle this graphically. So here is t equals 3. Here obviously is 0. So we need to find this area. And I'm going to divide it up into 2 trapezoids. So trapezoid number 1 is going to be in blue here. And trapezoid number 2 will make green. Okay. So I'm finding these areas geometrically. So we have a height of 2, a base of 1200, and a base of 1000 for my blue trapezoid. I'm just reading these numbers off the graph. So I'm going to do 2 times, so that's my height, 1000 plus 1200 over 2, and that's the area of a trapezoid. 1/2 b1 plus b2 times the height. And then plus the area of my second trapezoid, which is going to be a height of 1. My first base is going to be 1200 again. So that's this point in the graph. Plus my second base is going to be here, right? That was the hardest one to see, I think. 1200 plus 800 all over 2. Okay. So just to be clear, this expression I wrote down is equal to this integral. And then I'll simplify that. So notice These cancel out. I get 2200 plus half of 2000, 1000. It's 3000. Okay, so 3000 is my integral. I'm not going to write it right there. Actually, I'm going to write it like this. Now, here's the hardest thing, like reasoning-wise, for this. 3000 is not the total number of people in line, right? 3000, let's describe that number. It's the total number of people that got in line over 3 hours. It's the sum of all the changes in the amount of people in line. What we have not used is this 700 people. Okay, so 700 people are the number of people in the ride at t equals 0. And then we're adding 3,000 people to that. So the actual result here, the solution that we're looking for, is 700 people plus this integral, right? So this is an initial value problem. Okay, so we want to add 700 to our result, and that's going to get me 3,700 people in line. In line when? At t equals 3. Hopefully they fix this ride soon. Okay. So we have this function g now. This one is on the easier side, and it's easier than it looks. So if you're thinking it looks kind of challenging, it maybe looks a little harder than it is. So we want intervals where g is decreasing. We just have to be very careful about how we interpret this graph. So g is decreasing. We should think that means g prime is negative. Well, g prime, if we take this derivative, g prime of x, the derivative of 5 is 0, so we can ignore that. And then the derivative of this accumulation function is just f of x. So really, we want to say g prime of x is just equal to f of x. So we want intervals where f of x is less than 0. There's only 2 intervals here, right? And let's pay attention to our graph here. So our intervals are going to be from -3 to 0. And if I want to be really precise, I want to not include 0, but include -3. And over here, right? So from 12 to 15. And those are my decreasing intervals, because those are where the derivative is negative. Notice it was not the part of the graph of f that was decreasing, right? So again, taking this derivative was important here. Okay. And last one. This is the scariest looking one for sure. So we want an equation for the line tangent to the graph of y. And y is this accumulation function where x equals -1. So we need to figure out what y prime is. Y prime is the derivative. The derivative of -3 is 0. We have this negative, right? So we're going to keep that. And then, instead of 3, it is a 3. The derivative of e, so the -t to the third is e, or the derivative of the integral of e to the -t to the third is e negative x to the third. Okay, Now, if we want this point, we're going to plug this in. So I could write that like this: y prime of 1 equals negative e to the negative 1 to the third, which is 1 over e, right? Because this just becomes a 1, but it is negative, so we're going to move it to the bottom, and then we're going to keep the negative. Okay. So that is y prime of 1. And then let's think about what we just found here. This is the slope of our tangent line. Okay. So what I would maybe do here is look at these equations and eliminate everything that does not have the correct slope, right? So this one has a slope of negative 3e, wrong. Negative e is my slope here, wrong. This one has a slope of 0, wrong. Negative 1 over e is what we want, right? So that one is in the running, and then this one, 3e again, wrong. Okay, so it has to be d by process of elimination. And I don't need it. What I would want to do if I had more than one option with the correct slope is I would want to check if this point satisfied this equation, right? Because that would be the difference between a tangent line versus just a line parallel to that tangent line. But since only one has the correct slope, we can just conclude that D is the correct answer here.